学姐对你这事蛮你要跟我穿那种，你好色。好。
Alright, so
okay, we'll continue to prove theorem 2.4.b. Okay, we finished the justification that the vector addition inherit from the original vector space is closed in span of S. So it's closed. To showing that if we have UV in the span, then their sum is also in the span. Okay. And so the next thing is that with the same scale multiplication as in the original vector space V, that this product is also in span. If U is in the span of X and the alpha is a scalar. Okay. So so since U is in the span of X, so that U is equal to beta 1 plus beta 2 U2 plus beta M UM for some vectors in U1, U2 up to UM in S, and there are scalars like beta 1, beta 2 up to beta M, R. Right, so we have that. So now that's alpha U comes to alpha beta 1, U1 plus alpha beta 2 is equals to the alpha beta N UM. Okay, so actually we use the distribution law of scale multiplication as well as the associative law of scalar multiplications. So we actually use axiom 5 and axiom 6 for a vector space mentioned before. Because we gave 7 axioms, right? And so I skipped a little bit. Do you need me to to develop it in detail? No. If you need me to do something, raise your hand. I can do it right now, quickly. Yeah, okay. So, good. I will do it. So now I replace the alpha is here, right? So it's beta 1, U1 plus beta m, Un. Okay, so now it's here. And now by distributive law, then I will beta plus alpha beta m Um by xm. I think by xm distributive law is 5. Let me check it. Sometimes I forgot I need a reference here. Yeah, distributive law is the 5th. Great. Alright, so this is xm5 here. And then I will use associative law, so I can multiply alpha and beta first. Let's go to U1 plus alpha beta n, go to Un by xm 6. The associative law for scalar multiplication. Okay, so now alpha u is expressed as a linear combination. So which is a linear combination of vectors in S, because U1 up to Um are vectors in S. So this is linear combination. So that's alpha u is in the span. Okay. Right, so to prove the claim. Okay. Yeah, so whenever sometimes I skip some steps, let me know. I will do it in detail, okay? Maybe something is more helpful for you. All right. Okay, so we proved that the original vector addition and the scalar multiplication in V still has closure property in the space, all right, by using these two claims. All right, so they are well defined. Now, we can review the first axiom. The first axiom is the commutativity property of vector addition. And it is true in V, so it must be true in the span of X. Of course, so it can inherit X and Y immediately. Now, how about the XM2? So you can review the list. So let me take my notes here. How about the associativity of vector addition? No problem, right? Because when we have associativity XM, we of course X, because all the vector in span X is in V, so no problem. We have the property. Now, the question is the zero element. Is the zero element in V still now is in the span of X? Okay, so we have to check. Now this is we need to check it. All right, so the third part, since 0 V is equal to 0 U for any U in S. Okay? Because we prove a theorem I forgot the number of the theorem. Anyway, so 0 scalar multiply with any vector is go to the 0 vector, right? And I use the subscript to denote that this is the 0 vector of V. As we know, we proved that the 0 vector is unique. It's unique. We proved that before. So we deliberately should denote this 0 is for the original vector space V. And then 0 times U for any U. Right? And 0 times U is a linear combination of a vector U in S. Because this is scalar, this is a vector in S. So it's a linear combination with only one term. Okay? So that we say that it's in the span of S. Okay, so we show the 0 element, the 0 vector in the vector space V is also in the span S. So of course the space has 0 vector. Right, so it has axiom 3. And the axiom 4 is about the additive inverse. No problem, right? Additive inverse. So what is additive inverse? Think minus 1 U is the additive inverse of U. Alright, so let me see. So for each for a vector U in S in the span, okay, so for a vector in the span S, okay, we have U equal to alpha 1 U1 plus alpha 2 U2 plus alpha n UN for some U1, U2 up to UN in S, and alpha 1, alpha 2 up to alpha n in R. Okay. Now, the additive inverse of U in V is minus 1 U, right? We proved that in the previous theorem. So we multiply minus 1 with U is just the additive inverse. Okay? But as in here, okay, we can do it again as in the proof of the claim. So we have minus alpha 1 U1 plus minus alpha 2 U2 plus minus alpha m UN. Okay? Which is also a linear combination of vectors u1, u2 up to um in S. Thus, is also in the space. So, for every vector in the span, it has additive inverse. Because this is the additive inverse in V, but we prove that the additive inverse is also in the span S. Okay, so we have XM3. XM4. Okay, and so here I have to mark that. I forgot to. XM3. XM3 is about the existence of a zero vector. XM4 is about the existence of additive inverse. Right? So we have that. And how about the XM5? XM5 is about distributive law. But distributive law is true in V. So of course it's also true in the Spanish. Right. How about XM6? XM6 is about the associativity of the scale multiplication, right? And it is true in V, so also in the Spanish. And finally, the last one, the last one is about the unitary property. And the unitary property is true for every element U. So of course it's true for every element in the span S. Because the span S is a subset of V. Okay, so the fifth thing is that XMs 1, 2, 5, 6, 7, all right, can be inherited from V. Okay. Okay, so we finished, right? Because we proved that the vector addition scale multiplications are closed on the span of X. And we also proved the 7 axes are fulfilled for span X. So everything has been checked. So the conclusion is the span of S is a vector space. Okay? So that's the end of that. All right. Any questions? All right, so next we give another definition. Right, so let's read the vector space over R. Okay, a subset W of V is called a subspace of V if W itself is a vector space. Okay? So whenever a subset W of a big space is itself a big space, then this subset is called a subspace. Example 1. For any m times n matrix A, the kernel of A, of course, is contained in n-dimension Euclidean space Rn. Of course. Now we have shown by one of the example we raised up, the kernel of A, we have shown that is a vector space. Okay, over R. So kernel of A is a subspace of Rn. Okay, so this is the first example. The second example is that Pn is a subspace of P. P is the set of all real polynomials. And Pn is the set of all real polynomials of degree less than or equal to n. And we show that Pn is a vector space, P is a vector space, so Pn is a subset of P, so Pn is a subspace. Third example. So consider a subset as of a vector space V. Then we know that span is a subset of V, of course. Now since the span of vector is itself is a vector space, and theorem 2.4.b in above. So this example, the span of X is a subspace of B. Okay. All right. Now we extend linear independency and the linear dependency about for vectors in Rn, like we defined that before for column vectors. We can extend the concept to arbitrary vector spaces. Right. So a subset X of a vector space V is linear dependent. Okay, if there exists a non-trivial relation, non-trivial linear relation. Sorry. Okay, so if there exists a non-trivial linear relation here, alpha 1, u1 plus alpha 2, u2 plus delta plus alpha n, un equal to 0 for some vectors distinct vectors. We want to choose vector up to 0 n in S and the scalars number 1 up to not all zeros. Okay? Right? So we have to be careful. A subset of X of a vector space V is linearly linearly dependent. If there exists a non-trivial linear relation, right? So, and this non-trivial linear relation is for some distinct, so the component thing distinct vectors u1, u2, un. So you can select n distinct vectors from the set X. And to form a non-trivial linear relation means that the coefficients are not all zeros. Okay? So non-trivial means that the coefficients are not all zeros. Okay? And this definition applies to infinite subset. The subset can be infinite, many vectors. So we say that such a sub, even though it is infinite, if we can pick up finite and many distinct vectors, so u1, u2, they are all distinct. You can pick up that. Only finite many can be one vector or two vectors, etc. Okay? Such that we can form a non-trivial linear relation like this one. Okay? And so the coefficients are not all zeros. Then this set is called a linearly dependent set. So this is a very general definition. Okay, for any vector space and for any subset. And this subset can be a finite subset or an infinite subset. Any questions about the definition? Alright? And now the set, the last sentence, the set X is linearly independent if no such non-trivial linear relation exists. Okay? So if you can't find any such non-linear, that's such a non-trivial linear relation. If you can't, then this set is called an linearly independent set. So as before, to prove a set is linearly independent, you have to prove by contradiction. Okay? This is the common practice. Otherwise, how do you know that you can't find why? Okay? So that is the idea when you need to prove the linear independence of a set, even though it is an infinite set. Okay, so I reinterpret this last concept. So I make a remark, and many times it's useful. So a subset is of a vector space V, alright, is linearly independent if and only for any linear relation in S, i.e. alpha 1 U1 plus alpha 2 U2 plus alpha n Un equal to 0. So if we form any arbitrary linear relation S where U1, U2, Un, I use n, okay, Un are distinct vectors in S, and the scalars alpha 1, alpha 2, up to R. Right? So for any linear relation, suppose we can establish a linear relation, and U1, U2, up to U1 are distinct. Again, distinct. If not distinct, then it's quite easy to establish a non-trivial linear relation. Why? Well, you just take a U minus U and it's all 0, right? Okay, you can pick up an arbitrary U from S and form a non-trivial linear relation. Okay? So it's too easy, right? So I have to ask you that the vectors are distinct. So if we have such a linear relation and U1, U2, U1 are distinct vectors, we must have alpha 1 equal to alpha 2 equal to 0. Then all the coefficients must be 0. Okay. Only 0. So it means that all the possible linear relations must be trivial. So a subset is linearly independent if and only if this subset can have only trivial linear relation. Not else. Not else. Okay, so now I will state an important theorem. 2.4.6 in the textbook. So let X be a linearly independent subset of a vector space. Right. Oh, by the way, I have to remind you. Sometimes my statement is more precise than the statement in the textbook. I don't know the authors. Sometimes they just write the statement. I think not well qualified. Okay. So I sometimes I rephrase or I give more conditions on the statement. Okay. All right. So let X be a linear independent subset. Now each vector u in the span of S, each vector u in the span of S has a unique representation as a linear combination of distinct vectors in S. Okay, I should put this thing. Yep. Okay, so to make things more precise, right? So that so if X is a linearly independent subset, okay, and so satisfy your connection here, then each vector in the space of X has a unique representation of a linear combination of distinct vectors. Of course, every vector in the span of X, right? By definition, every vector u in the span of X is a linear combination of distinct vectors, of course, right? Because this is the definition. And the importance of this theorem is that if S is linearly independent, then any linear combination of distinct vectors, right, they are all different. So it is impossible for you to have two different linear combinations of distinct vectors to be the set to be equal. It's impossible. Okay, so this is called a unique representation. So once you write down a linear combination of distinct vectors in X, then this vector in this way must be a unique vector. There are no other vector in the span can take the same form. Okay. So let me prove that. And but before that, I give an example. So okay, I take a simple example. Right, so X is a linearly dependent set. Subset of R2. Things. Why this set is linearly dependent? It's because that when you add them together, minus, right, 1 minus 1 is equal to 0, 0. So this is a non-trivial linear relation. Okay? A non-trivial linear relation. So this set is linearly dependent. Okay, so now we see that this vector is in the span of S. Why? Because this vector can be written in this way, minus 2, 1. Okay? So of course it's in the span of S, of course. But it has another representation because that it is 2 times this vector. So the same vector in the span has 2 different representations as linear combinations. Okay? So this is very common. This must be true for any linearly dependent set. The theorem tells you that whenever the S is a linearly independent set, then this situation never occurs. Never. Okay. Or maybe that's the representation of 2 minus 2 as a linear combination of distinct vectors in S is not unique. Okay. All right. So I will do the proof of the theorem. All right. So assume that U is in the span of S such that we have 2 representations. U can be written as alpha 1 U1 plus alpha 2 U2 plus plus alpha R UR plus alpha R plus 1, and now V1 plus alpha n Vn minus R. This is one representation, and also we have another representation. It's beta 1 U1 plus beta 2 U2 plus plus beta R UR plus beta R plus 1 W 1 plus plus beta M and W and minus R. Okay, where U1 up to UR, V1 up to V and minus R, W1 up to W and minus R are distinct vectors in S. Okay, and alpha 1 up to alpha n, beta 1 up to beta n are R. Alright, so here is that we make an assumption that there exists a vector in the span such that we have two representations as linear combinations of vectors in S. And here we say that in this list that the vectors pick up from S may have common vectors. So for here I account for same vectors here. Okay, so they may have the same vector here, but with maybe different coefficients. And the rest of the vectors are all different. Okay, so this is the most general situation. If you have 2 representations as linear combinations of distinct vectors X. So if you have a question about why I write it this way, please raise your hand. So no problem, right? Good. All right, so we have this situation. Now, the 0 is u minus u, right? So I make the subtraction. So now I have, so we have a alpha 1 minus beta 1, u1 plus theta, plus alpha r minus beta r, ur, plus alpha r plus 1, u1 theta, plus alpha n, un minus r, minus beta r plus 1, w1 theta, minus beta m, w and minus r. Alright, so I just write it down here. Which is a linear relation, right? So which is a linear relation, right? Linear relation of distinct vectors. In S. Right? So I, from the subtraction, I obtain a linear relation, right, of vectors, distinct vectors in S. But S is the linearly independent set. So any linear relation should be trivial, as I make a remark here, right? So since X is linearly independent, any linear relation in S must be trivial, i.e. trivial. What does that mean? Means that all the coefficients must be zeros. Okay, so i.e. alpha 1 minus beta 1 equal to alpha r minus beta r, it's 0 equal to alpha r plus 1, equal to alpha n equal to beta r plus 1 equal to beta n. They are all zeros. Okay, so now they are all zeros. They are all zeros. So they can be neglected. And alpha 1 is equal to beta 1, alpha 2 is equal to beta 2, and alpha r is equal to beta r. So exactly these two, originally it apparently different, right? But in reality is that these two expressions is the same. Right? These two, they are the same, right? The original appearance is different, right? It seems like different. Yeah. But the conclusion is that these two representations exactly are the same. So it gives you surprise, right? Surprise. And so that's the two representation. Given above are the same. Okay, and so the theorem is proved. Okay, so let's take a break. Okay. All right. So I myself regard these three theorems as simple theorems, so you can understand the statement of the theorems as well as their proofs. So the next theorem I want to discuss is about 2.4.10. Okay, so let's be a subset of n vectors in a vector space, which so suppose from the vector space I pick up n vectors. Of course, to form a set, we say that the size n means that we have n distinct vectors. So we understand that. Now, then every set of more than n vectors, more than n vectors in the span of X must be linearly dependent. So let me say again, I pick up n vectors from a vector space to form a set X. Then I use this n vector to span subspace, right? We already know the span of vector is a subspace. And then then if I take more than n vectors from this subspace, okay, then this set must be linearly dependent. So from the statement, you know it is a non-trivial result. Okay, so with the proof. So let X equal to V1, V2 up to Vn. Okay, so X is a set of n vectors. And the let m greater than n, and we pick up U1, U2 up to Um vectors in the span of S. Okay, so we pick up m vectors, and m is bigger than n, right, from the span of S. Because they are in the span of X, then we have, okay, so we have now U1 is equal to B11, B1 plus B12, B2 plus plus B1n, Bn, and up till Um, so this is B1m. Okay, so okay, and the V1 plus B 2m into plus b 2. Oh, so okay, I'm sorry. The second part, the second index for the index of the u. So p1, 2, 1, and 1m, 2m, and 1m. Yeah. It's for my data purpose, so I index the coefficient this way. Okay, sorry. So this is 1, 1. 1 is in here. 1, 1, 2, 1, and 1. Okay, for the u1. And for um, I have 1m, 2m, and n. Okay? Right, so now I pick up. And to show, so our purpose is to show that u1, u2 up to um is linearly dependent. Right, this is our purpose because the statement says that this set must be linearly dependent. We will find non-trivial non-trivial linear relation. x1, x1, u1 plus x2, u2 plus theta plus xm, um equal to 0 with the x1, x2, theta, xm, not all zeros. Well, we have to find, so I put x means unknown, right? I haven't found yet, but I try. I try to find a non-trivial linear relation. Okay, it means that I try to find coefficients x1, x2 up to xm, such that this coefficient not all zeros. This is my purpose, right? Alright, so, but I know my target, so I will try myself to reach to a target. Okay, so now from here, this is my purpose. Alright, so now 0 is the sum on I from 1 to m, and xi and ui. Okay, so I want to find. So to find the xi, right? So let's see. And each ui as this representation, summation j from 1 to n, and we have b, ji, and the region. Okay, here, just do the substitution. Okay, and then I exchange the summation. So I have to b, ji, xi, of I from 1 to m, and bji xi to the result. Okay. So I sum j first, and I sum I first and then the j. In here, we sum j first and then sum over I, but we can exchange that. Okay, and so Vj is here, and this is that. Okay, now B, the Bij, they are known, right? Because they are given here, but they are in the space. But the Xj is unknown. All right. So we want to establish such a relation. Okay, so our goal is to find x1, x2 up to xm, not all 0, such that the inner sum they are all zeros for all j from 1 to n. Okay. So to reach to here, if I can find the xi's, not all zeros, such that the inner sum are all zeros, then all zeros, 0 times Vj is equal to 0. Okay. So we establish a non-trivial linear relation. Okay, for the UIs. Alright, so we turn the target now. So our purpose is just, well, to find x1, x up to this one here. But so it's a linear system, and it's actually, this is a system of homogeneous linear equations. So I put it in a matrix form. So this is B11, B12 up to B1n, B21, B22 up to B2m, Bn1, Bn2 up to Bnm, x1, x2 up to xn equal to 0, 0, 0. Alright, so we want to solve, so it is equivalent to solving this homogeneous linear system. Okay? And now it's clear. If the kernel of this coefficient matrix is not trivial, then we can find a solution, right? Not all component zeros, right? To satisfy this linear system. Okay? Alright, so think n is less than m. So we have m columns and we have n rows. So we have more columns than rows. And the rank of this matrix is the minimum of, is less than or equal to the minimum of n and m. Okay, so we see that the rank of the coefficient matrix is equal to maxima of minimum of and which is n. And the rank of the coefficient, the number of pivots, okay, number of pivots in the reduced echelon form of the coefficient matrix. And it's also equal to the number of pivot positions in the matrix here. So the number of pivots is less than or equal to n. So they are, but we have more columns. So some columns may not have any pivot. Okay? And when for those columns without pivot, the corresponding variable can be set to be free variables. And then we have a lot of solutions. Actually, infinitely many solutions already. Right? So let me write it down. So they are at least m minus n columns of the coefficient matrix without a pivot. So they are at least m minus n out of the n unknowns x1, x2, x2, xm can be selected as free variables. Okay, so we get to the point right now. Everything is clear already. Okay. So that's we have a non-trivial solution for x1, x2, up to xn. So this shows that the set U1, U2 up to Um is linearly dependent. Okay, so we're done. All right, so let me describe the story, the whole story again. To show that this m vectors taken from the span of x to be linearly dependent, we should find a non-trivial linear relation, right? Such that the coefficient x1, x2, up to xm, not all zeros. We have to establish such a linear relation. And now we look at into the deep inside to say, once we have to have such a linear relation, right? Then we have to see what happened. How can we make up such a solution? Then by substitution, we find that we discover that if we can find xi such that the inner sum of zeros, then of course this is the zero vector. So we establish a linear relation. So the goal becomes to find x1, x2, xn, not all zero, such that the linear equations, we have n of them. We have n linear equations, right? To be satisfied. And together, to solve the n linear equation, just to solve the homogeneous linear system. Alright, so to find a non-trivial solution for the linear system, once we find such a non-trivial solution, then go back to here, everything is satisfied. So we will find a non-trivial linear relation. And then this set is linearly dependent. Okay, so we push back. Okay? And now, at this point, then we will apply our knowledge learned up to now in solving homogeneous linear system. And here, because we have more columns than rows, so that some columns has no pivot. Right? That is a crucial point. Once we know that, then all the columns, the corresponding variable corresponding to column without pivot, can be said to be free. Okay, so we have at least n minus n free variables. So we have infinitely many solutions, non-trivial solutions at all. So we handle them. Okay, but we are not greedy. Just one is enough. So we say we have a non-trivial solution. Okay. And then, so this works, right? And then over here, we can find a non-trivial linear solution. So it exists, and then we're done. Okay? So this approach is very direct. We push forward, push pressure up to the deep inside. Okay, and then find the core. Right? Find the core. And then apply our knowledge. All right. So the next theorem has a very good consequence. So let me state the theorem first. So let X be linearly independent subset of a vector space V. If I find a vector in the vector space V, and I find that V is not in the span of S, okay? Then I can join the V to S. So then the union, okay, join together. So this set configured is linearly independent too. All right, so this theorem is important. You can enlarge a linearly independent set by this theorem. Okay? So, remark. So the above theorem can be used to construct a linearly independent set. The subset in a vector space. Right? So you can. So first of all, you can pick up a non-zero vector, right? In with non-zero vector. Because if we pick up a zero vector, this zero vector should be linearly dependent. Because you know, if S is the set of zero vector, then it's linearly dependent. Why? Because I have 2 times 0 is 0. So I have a non-trivial linear relation. This is a non-trivial linear relation because the coefficient is non-zero. So I establish a non-trivial linear relation. So it's dependent. It's easy, right? So that I can't pick up but for any non-zero vector, then but if but this one is linearly independent. But only if U is not equal to 0, right? So if U is a non-zero vector, then the singleton, a set with one element is called a singleton. Right? A singleton is the name to describe such a set. So a singleton means a set with only one element. Okay. So this singleton is linearly independent if and only if U is non-zero. So I can start, because I want to construct a linearly independent subset, right? So first of all, I pick up a vector non-zero, right? So initially, the set consists of one vector. And then I construct the span of X, okay? and see that, and then from, so every time, so this is V, and here, I draw a better picture. Sorry, but this is V, alright, usually, and this is the set X here, and so that the span is 1, and when the span, when I draw here, means that the span is not equal to V, so I can find a vector V here. So V is in capital V, but not in the span. Then I can join this V into S. All right, and then the new set also linearly dependent. Okay, so that's the idea of the. And so with that, then you can add one element into S, so that you can form bigger and bigger and bigger linearly independent subset. Up to a point, you have to start when the span of X is equal to V. If the span of X is equal to V, then you have no more vector can pick up, right? Because the span of X, the S span the whole vector space already, so you have no other selection to do. Otherwise, you can continue the process. Okay. So in some cases, you can construct an infinite linearly independent set, because you can add vector one by one indefinitely. It's possible. Okay, it's possible. For example, the vector space of all real polynomials. Okay, and then, so first of all, you pick up the constant polynomial 1 into S. Original S is the empty set. So you pick 1, the constant polynomial into, so it's linearly independent. And then, the span of 1 is just constant polynomial, arbitrary. So you pick up a polynomial of degree 1. What is that? It's x. Right? So first of all, you put 1 and then x. X is a linear polynomial. And the span of 1 and x is just a polynomial of degree less than or equal to 1. So you pick up x squared. X squared is not in the span of 1 and x. Okay? And so you pick up x squared. So now 1x and x squared is a linearly independent set. Alright, so you gradually and then indefinitely. And this set is a linearly independent set. Okay. So maybe I make an example before I prove the theorem. For example, in P, right? So in P, okay. First of all, initially, we have S equal to the empty set. Empty. Alright, so step 1. Alright. Select 1 in P into and join S such that S becomes to, okay, so the assignment. Right? And step 2. Once you have, okay, step 2 is that apparently x is not in the span of s, which is span of, this is p and 0. P0 means that all constant polynomials. So x is not in P0, alright? But x is indeed in P. So S union of x. Right? So we join to replace x. So now x consists of 1 and x. And we can step n. Okay. So that here s is equal to 1 and x. Right. And so you do that in step n, that xn is not in the span of x. This is the span of 1 x. X minus 1. 1. Yep. 2. Oh, n plus 1. Sorry. Step n plus 1. Yes. Alright, so now here, because the span of 1 up to x minus 1 is a polynomial of degree less than or equal to n minus 1. And the xn is also in P. So now it's union of xn. And it continues to do so. So the end is that, so this shows that the set xn power is a linearly independent set, dependent subset of P. So from this example, we can construct an infinite set which is linearly independent. Okay, so the proof of the theorem. Alright, so prove that by contradiction. So assume. So suppose that S union is linearly dependent. Okay? So suppose this set is linearly dependent. Okay? So there exists U1, U2 up to UN in the set such that alpha 1, U1 plus alpha 2, U2 plus alpha m, UN is 0. Right? For alpha up to alpha m, not all zeros. Alright, so means that we have, this is a non-trivial linear relation. Okay? Because we suppose that this set is linearly dependent. So we have that. Okay, so we must have UI equal to V for some I. So in this list, U1 up to UN, we pick up from this set. One of them must be U. Why? If U1, U2, or UM are from X, all from X, then this is a non-trivial linear relation in S. Then it's a contradictory to the assumption that S is a linearly independent set. Right? So otherwise, U1, U2 up to UM must be in S, and alpha 1, U1 plus alpha m, UM equal to 0 is a non-trivial linear relation in S, which is a contradiction. Okay? It's a contradiction to linear independency of S. Because we assume S is linearly independent. Alright, so you can't have this situation. So one of them, U1, U2 up to UN must be equal to V. Okay, and with the reason, with the same reason, alpha I must be non-zero. Even though UI is equal to V, But also, alpha I, the coefficient of ui, should be non-zero. Because if it's 0, then you can move out the term, right? Okay. So, or I just, if you, maybe I write it more explicitly. Also, we must have alpha I not equal to 0. Otherwise, alpha 1 u1 plus alpha I minus 1 ui minus 1 plus alpha I plus 1 ui plus 1 plus alpha m um equal to 0. Okay, is non-trivial. Linear relation again. So conduction 2. Okay, so again, contradiction. So the alpha I should not be 0. Okay. Okay, so now we have nowhere to go, right? So we have alpha I, V, alpha V, because ui is equal to V, right? And the alpha I is non-zero. So alpha I V is equal to minus alpha 1 u1 minus alpha I minus 1 ui minus 1 minus alpha I plus 1 ui plus 1 minus alpha m um. Okay, so we can move the other terms to the right hand side. Okay, and so we divide both sides by alpha I because alpha I is non-zero. So v is equal to minus alpha I u1 minus alpha I minus 1 alpha I ui minus 1 minus alpha I plus 1 divided by alpha I ui plus 1 alpha m divided by alpha I us, which shows that V is in the span of S because it's a linear combination of elements in S. Once again, a contradiction because we already said V is not in the span, so a contradiction. So now we encounter a contradiction again, and we know where to go. Since because we suppose this set is linearly dependent. So once we give the assumption that this set is linearly dependent, then we go over all possible trace and then know where to go because we will encounter contradiction eventually. So that says that this premise is incorrect. Okay, so S union V is linearly independent. Okay, so this is the end of the proof. All right. Any questions? Okay, I have some time to write a definition. Let V and W be two vector spaces. A function f or t, that is t, right? A function t from v to w, okay, is called a linear transformation. From v to w if I have a linear combination in V, then the transformation, the map by T, will go to the same linear combination with the same coefficient. But the U and V are replaced by their images under T. And for all U, V in V, and alpha, beta in R. Okay. So this is simply a generalization of linear transformation from Rn to Rm, right? This is because before we just consider linear transformation among Euclidean spaces. But now the same concept can be extended to arbitrary vector spaces. Okay, so same situation here. And the following theorem gives us a tool to verify whether a function could be linear transformation. So I just state the theorem. Maybe I have no time to prove it. Okay, so let T be a function. So first of all, it's a function from a vector space V to a vector space W. Alright, so first of all, T is just a function from a vector space V to a vector space W. Then T is a linear transformation from V to W if and only if for all, if only if Tx plus y equal to Tx plus Ty and T alpha x equal to alpha Tx for all x, y in V and alpha. So I split the checking of whether T is a linear combination, but it's a little bit complicated because I have to check all the linear combinations like this one. I just take two things which are much more simpler. First of all is that if I sum them together, I sum two vectors in V together and then make the transformation, and if I found that this is the image is just the sum of the respective images. And this is much even more simpler. The image of alpha times x is just the alpha times the image of x. So much more simpler. Okay, so this is the oh, by the way, I think I have two minutes. Maybe I can finish my proof. It's so simple. Okay. All right, this way, the forward direction. All right, so to Tx plus y. Tx plus y can be represented as a linear combination with coefficient 1, right? So they have all the coefficient 1. And then, so this is 1 Tx plus 1 Ty. And why we can have this one? We use the axiom 7, right? The unitary property. because x is equal to 1 times x. So we use axiom 7, right? And this is from because t is linear transformation. Okay, and so this is tx. So we use axiom 7 again in W, so that we have that. So we establish this. And second thing is that this T alpha x. So what's T alpha x? Well, T alpha x plus 0x. Okay? Okay, maybe I will do it one by one. Okay, so I can add a 0. And this 0 is in V. Specifically, alright? It's in the fixed V. Because this is the 0 element. And then I use a theorem. The 0 is, maybe I can put a 0 here and the x here. Okay? So 0 is the scalar, x is this x. And we prove theorem that the 0 times any vector is the 0 vector. Okay. And so, because by linearity, we have 0, okay, linearity. And once again, apply the theorem, 0 times an arbitrary vector. Here, x is 0, but this 0 is the 0 in W. Okay, this is W. And because this is 0 in W, so we have alpha tx. Okay, so we finish, right? We check. If t is linear, then tx plus 1 is tx plus t1. And t alpha x becomes alpha times tx. Reverse direction. Suppose we have these two properties. So now we check. So t is, we regard our x as a vector, beta as a vector, right? So it's the sum of two vectors. Now apply this rule. So this is t alpha x plus t beta 1. Now apply this rule. This is alpha tx plus beta t1. Okay, and we have that. So complete the proof. Okay, so we have this auxiliary theorem. Okay, theorem that, and this tool will let the checking of linear transformation to be much more easier in many situations. Okay, so I raised this point. Okay. So I have to stop here. And I'm supposed to finish this section, but a little bit. So I ask you to read the textbook. Okay? Because next week we have a quiz on the whole section, 2.4. We are approaching to the midterm, first midterm. It will be November, I think, November 4th. Okay? The first meeting will be November 4th. It's coming. Okay, so that's it, and I'll see you next week.